And today we're talking quantum computing.
Yeah, it sounds a bit like science fiction, doesn't it?
It does. It really does. But we've been looking at some incredible material on this, specifically a speech that paints a pretty clear picture that this is, well, it's not sci-fi anymore.
Yeah, it's becoming very real very rapidly. And I think our goal here is to give everyone a clear picture.
Exactly. A clearer picture of its power and, what it could mean for all of us for the future. And you don't need, like I said, you don't need a physics degree or anything like that.
Exactly. We're diving into this speech titled The Quantum Horizon, Charting the Next Revolution in Computation.
Okay.
It's fascinating stuff. Gives you a really compelling perspective on what might be the next big jump and how we as humans deal with information. It really gets into the convergence of physics, math, and computer science.
Yeah, and that's a really interesting way to look at it. It's not just one thing. It's this merging of these different fields.
Yeah, and I think what we really want to do is get at what makes this technology so different from what we have now.
Right, right. And why there's so much buzz about it, why people are getting so excited.
Absolutely.
So I'm going to guess when you hear quantum computing, you think, oh, okay, faster computers.
Right.
That's kind of the initial thought.
More powerful. More of what we have. Yeah.
But what this speech makes really clear is that it's not just about speed. It's so much bigger than that.
Oh, absolutely.
Yeah.
It's a totally different way of thinking about computation.
Right. It's like a fundamental shift.
Right.
But to get there, the speech starts by grounding us in, the basics, the good old bit.
Yeah. The bit, the 0 or 1, the foundation of everything digital we have today.
Yeah.
Classical computing, as incredible as it is, it's all built on that system, binary.
Right.
Quantum computing, though, it introduces this totally new building block, the qubit.
The qubit.
Okay. And the cool thing, as this speech points out, is a qubit, it's not just a 0 or a 1.
Right, right.
It can be both at the same time. It can be in what's called a state of superposition.
Oh, okay. So, it's not one or the other. It's both.
Oh, yeah.
How is that even possible?
Well, the speech uses this great analogy, actually. It says, think of a dimmer switch.
Okay, a dimmer switch.
Instead of just an on or off switch, right?
Right.
So the qubit, it's like that dimmer. It can be anywhere in between. All those shades of gray existing at the same time. So a single qubit, it's not holding just one piece of information. It's juggling all these multiple possibilities at once.
Oh, wow. So it's not just one thing. It's all of the things at the same time.
Exactly. And that's where things start to get really interesting.
Okay, so what does that mean for actual computing, though? How does that change things?
Well, it changes things a lot. Because this ability, this simultaneous exploration of all these possibilities, it's just exponentially beyond what classical computers can do, at least for certain types of problems.
Oh, okay. So it's not that it's just, faster across the board. It's that it can do things that traditional computers can't even, conceive of.
Exactly. And then on top of superposition, we have entanglement.
Okay, entanglement. Another one of these quantum phenomena, I guess you could say.
Right. And the source, this speech, really highlights how crucial it is. So entanglement is this weird interconnectedness between qubits, where if you change one, it instantly influences the other. Doesn't matter how far apart they are.
Wow, so they're, linked, no matter what?
Yeah, it's like they're linked, but it's instant.
Wow.
And that's why Einstein called it spooky action at a distance.
Spooky action at a distance. I like that. That's a good way to put it.
Yeah. And it's that spookiness that lets quantum computers do these amazingly powerful things.
Oh, okay. So I'm trying to picture this. I'm trying to wrap my head around it. If you have a classical computer trying to solve a maze.
Okay.
It's got to try each path one at a time.
Right. Sequentially.
But a quantum computer with superposition, it's trying every path all at once.
Exactly. And then with entanglement, if one of those paths hits a dead end, all the others instantly know.
Oh, wow. So it's learning as it goes, but it's learning instantly.
Exactly.
Ew.
It's not just speed. It's a whole new way of thinking about problem solving. It's operating on probabilities. It's interconnected.
Yeah.
Unlike those zeros and ones in classical computers.
Right. So it's not just a faster horse, it's a completely different animal.
Exactly. And the speech is clear about what this means. It means quantum computers could solve problems that are just impossible for even the most powerful supercomputers we have now.
Oh, wow. So there are problems that are just computationally intractable. They're just too complex for traditional computers to even attempt.
Right. Things that would take literally the age of the universe to solve.
Oh, wow.
Things like really complex simulations or factoring these massive numbers, the kind used in cryptography, or super intricate optimization problems, all stuff that's just way beyond classical methods.
Okay, so it's not just faster, it's capable of things that we can't even do now.
Right. And the speech makes this point that it's not even just about doing what we do now, but faster. It's about doing totally new things, solving totally new kinds of problems.
Right. So it's not just about, getting from point A to point B quicker. It's about going to completely different destinations.
Exactly. Destinations we couldn't even imagine before.
Yeah.
Especially problems that mirror how our universe actually works, at that quantum level.
Oh, okay. So like problems that are inherently quantum mechanical in nature.
Yeah. Think about accurately modeling how molecules behave or designing materials at the atomic level. Those are inherently quantum problems.
Right, right. So it's like the tool is finally matching the complexity of the problems we're trying to solve.
Yeah, that's a good way to put it. And the source, the speech, does a great job of then transitioning from the theoretical to the practical.
Okay.
It lays out some of the early but really promising applications of quantum computing across all these different fields.
So early days, but we're already starting to see glimpses of what this could do.
Exactly. The source calls them early glimmers of transformation.
Okay. I like that. So let's dive into some specifics. Where are we seeing these glimmers?
Well, let's start with drug discovery and medical research.
Okay, drug discovery. Makes sense. That's a very complex field.
Very complex. And the source points out how hard it is for classical computers to simulate how molecules behave. It compares it to trying to predict the weather months in advance by tracking every single air molecule.
Oh, wow. Yeah, that's pretty much impossible.
Exactly. But with quantum computers, well, the promise is that they could model these intricate interactions with way more accuracy.
So we could actually simulate how drugs work at a molecular level.
Yeah, and not just simulate. Design new drugs.
Yeah.
Atom by atom.
Whoa. Okay, so like we could actually build the drug digitally and see how it interacts with the body before we even synthesize it in the lab.
Right. You could predict how effective it would be, what side effects it might have, all through simulation.
And that would just speed up the process of developing life-saving treatments so much.
Absolutely. Think about it. New treatments for cancer, Alzheimer's, new viruses, all potentially years faster.
Yeah, that would be huge. And the speech goes even further. It talks about personalized medicine.
Right. Imagine simulating how a drug interacts with your specific biochemistry, your individual DNA.
Oh, wow. So it's tailored medicine. It's not just a one-size-fits-all approach.
Exactly. It's treatment optimized just for you, minimizing side effects, maximizing the positive outcome.
That's a whole different level of healthcare. And it's not just medicine. The source talks about materials science too, right?
Yeah, that's another big one. The materials that make up everything around us. And the source explains that at the core, how a material behaves, its properties, they all come from quantum interactions at the atomic level.
Right. So it's all about how those electrons and atoms are interacting.
Yeah. And right now, finding new materials with specific properties, it's a lot of trial and error.
Right, right. It's like you try things, you experiment, and you hope you get lucky.
And it's slow. But with quantum computers, the source says, we could design materials from the ground up.
Oh, wow. So instead of, stumbling around in the dark, we'd have a blueprint.
Exactly. We know what to build at the atomic level to get the properties we want. The source has some amazing examples.
Okay, like what?
Things like high-temperature superconductors.
Oh, right. I've heard of those. Like, they can conduct electricity with zero resistance?
Right, and that could revolutionize how we transmit energy. No more loss in power lines.
Oh, that would be huge.
Then there are catalysts for clean energy.
Oh, okay.
Things that can capture carbon from the air or make fertilizer using less energy.
Yeah. So helping us combat climate change and produce food more sustainably.
Exactly. And even materials for way better batteries.
Oh, okay. Like longer lasting, faster charging.
Yeah, imagine a phone that lasts for weeks on a single charge. Or an electric car that can go 1,000 miles.
That's incredible.
And it all comes down to this shift. From blindly searching for a solution to knowing exactly what to build.
Right. And the source also talks about AI, artificial intelligence, and machine learning.
Right. And how quantum computing could completely change the game there, too.
Right. So how does that work? Like, how does quantum fit into the AI world?
Well, the source explains that a lot of AI and machine learning is about dealing with massive amounts of data,
Okay. Yeah.
finding patterns in it, optimizing really complex systems.
Right, and that takes a lot of computing power, right?
A ton. But there are these quantum algorithms that could potentially speed up those tasks enormously.
Oh, okay. So like specific algorithms designed for quantum computers that can handle these massive AI workloads.
Exactly.
Yeah.
So things like complex optimization problems or recognizing complex patterns or even sampling from complex probability distributions. All stuff that's really hard for classical AI. Quantum could do it way faster.
And so what would that mean for us? Like what would that actually look like in the real world?
Well, the source suggests it could lead to this whole new generation of AI.
Right.
Far more powerful than what we have now, able to tackle even more complex problems, like in finance maybe, or in climate science, making even more accurate predictions. Really any field where you have tons of data and complex systems.
Right. So it's like unlocking this whole new level of analytical power. But, it all depends on us actually building these stable quantum computers.
Yeah, exactly. And that's where the source gets real with us. It talks about the challenges.
Right, because it's not all just like sunshine and roses.
No, not at all. It describes the development of large-scale, fault-tolerant quantum computers as this, like scientific and engineering marathon.
A marathon. Okay, so a long, hard road ahead.
Yeah. And a big part of that marathon is figuring out how to actually create and control these qubits.
Right, the qubits. They're the foundation of all of this.
Exactly. And the source mentions that researchers are looking at all these different ways to make them, all these different physical systems.
Oh, so there's not just one way to make a qubit.
No, there are a bunch of different approaches.
Okay, like what?
So there are superconducting circuits. They use tiny electrical currents to create the qubits.
Okay.
Then there are trapped ions. They use lasers to control these charged atoms, the ions.
Oh, wow. That sounds complicated.
Yeah, they're all pretty complicated. There are also photonic qubits, which use light particles.
Light particles? Okay.
And topological qubits, which are even weirder. And then there are neutral atoms.
Okay, so lots of different options, but what's the best one?
That's the big question. And the source calls them qubit modalities.
Qubit modalities.
And it says that each one has pros and cons.
Okay, so it depends on what you're trying to do.
Yeah, it depends on how stable they are.
Yeah.
How long they can hold that quantum state, how easy it is to build a lot of them, how well they can talk to each other, and how accurately we can control them.
Right, right. So a lot of factors to consider.
Yeah. And the source says, we don't really know yet which modality will be the best. Or maybe it'll be some combination of different ones.
Oh, so like a hybrid approach.
Right. Yeah, maybe. It's all still very open.
And it's not just about making more qubits either, right? It's about making them better.
Exactly. It's not just quantity, it's quality.
And the source, it talks about this challenge of noise.
Right, noise and decoherence.
Okay, so what's noise in this context?
It's basically anything that interferes with the qubit, any kind of environmental interaction.
Oh, okay. So like vibrations, temperature changes, electromagnetic fields, all that stuff.
Yeah, all that stuff. And it can mess with those delicate quantum states. It can cause them to lose their superposition, their entanglement.
Right. So it's like the qubit gets disrupted and loses its quantumness.
Exactly. And that's decoherence. It's like the qubit's information leaking out into the environment.
And that's a problem because those quantum properties are what make them so powerful.
Exactly. And that's why the source highlights this need for quantum error correction.
Okay, quantum error correction. So like a way to protect the qubits from all that noise.
Yeah, it's like building redundancy into the system. You use multiple physical qubits to encode a single logical qubit, so it's more resilient.
Oh, okay. So it's like having backups. If one qubit gets messed up, the others can compensate.
Right. And this redundancy lets us detect and correct errors as they happen. But the source points out that error correction comes with a cost.
Oh, okay. So what's the catch?
Well, it takes a lot of physical qubits to make just one really good logical qubit. A lot more.
So we need to build even more qubits than we thought.
Yeah, basically.
Yeah.
And developing and implementing effective error correction is one of the biggest challenges right now.
Okay, so it's a hurdle, but if we can overcome it, the source is pretty optimistic about the future.
Oh, yeah. It paints this amazing picture of what a world with mature quantum computing could look like. It's not just about doing things a little better, it's a fundamental shift.
So like a paradigm shift.
Yeah, with really huge implications for society. And the impact would be felt across all sorts of industries.
So it's not just one sector that's going to be affected, it's everything.
Pretty much. The source specifically mentions finance,
Okay, finance.
Quantum computers could be used to optimize investment portfolios or to analyze really complex financial risks.
So, like, making better investments and predicting market crashes, maybe?
Maybe. And then there's logistics, optimizing delivery routes for, say, a global shipping company.
Okay, so making everything more efficient.
Right. And then, really importantly, cryptography.
Oh, right, cryptography. So how we secure our data.
Yeah. And the source points out that we'll need new encryption methods, quantum-resistant ones, because quantum computers could potentially break the encryption we use now.
Oh, wow. So that's a security risk we need to prepare for.
Yeah, absolutely. And on top of all that, the source says there will probably be whole new industries, things we can't even imagine yet.
So it's not just about improving what we have now, it's about creating things that don't even exist yet.
Right. And beyond specific industries, there's scientific research.
Okay, research. How would quantum computing affect that?
Well, it could change how we do science at the most fundamental level. Because suddenly we could analyze huge amounts of data and simulate really complex systems that we couldn't before.
So like in physics or chemistry or biology?
Yeah, all those fields. It could lead to a ton of new discoveries and help us understand the universe and life itself in a whole new way.
And the Force even connects this to solving some of the biggest challenges facing humanity.
Right. It talks about designing new catalysts that can capture carbon from the atmosphere, or developing new medicines for global health crises, or figuring out how to best use our resources on a global scale.
So it's not just about technology for technology's sake. It's about using this power to actually make the world a better place.
Exactly. And the source ends by looking ahead, giving us a glimpse of this quantum age.
Okay, so crystal ball time. What's in store for us?
Well, the source says that we'll probably see big advances in quantum error correction in the next decade.
So we'll be able to build those fault-tolerant quantum computers.
Yeah, hopefully. And then with better error correction, we'll be able to develop even more sophisticated algorithms. And we'll start to see what's called quantum advantage.
Okay, quantum advantage. So what's that?
That's when a quantum computer can definitively solve a problem that a classical computer just can't.
Oh, so it's not just faster, it's actually capable of doing something that's impossible for our current technology.
Yeah, that's the idea. And the source mentions Shor's algorithm specifically.
Okay, Shor's algorithm, what's that all about?
It's an algorithm that could break the encryption we use for things like online banking, secure communications, all that stuff.
Oh, wow. So like our current security measures would be completely useless.
Yeah, potentially. But the good news is that we're already working on new quantum-resistant cryptography.
Okay, so we're trying to stay one step ahead.
Yeah, exactly. And the source points out that a lot of big financial institutions are already investing heavily in quantum computing.
Oh, so they see the potential and they're trying to get a head start.
Yeah, they see it as a way to get a competitive advantage, maybe in things like financial modeling or predictive analytics.
So big changes coming to Wall Street, it sounds like.
Maybe, but it's not just about finance, of course. It's going to impact pretty much everything.
And the source seems to suggest that we shouldn't think of quantum computing as, like, replacing classical computing.
No, not replacing, more like augmenting.
Okay.
And the source even talks about this idea of cross-pollination.
Cross-pollination, okay.
Between quantum computing and AI. So we might end up with these hybrid approaches.
Okay, so like combining the strengths of both.
Exactly. So classical computers will still be important for a lot of things.
Right.
But quantum will add this whole new layer of capability. And the source envisions a future where quantum computing is just part of our infrastructure.
Right. Like just baked into how we do things.
Yeah, maybe accessed through the cloud initially. And eventually it'll be this essential tool for pretty much every field, from science to industry.
So it's not just a technology, it's a shift in how we think, how we solve problems.
Exactly. It's about harnessing the fundamental building blocks of reality to understand the universe and to create new things.
So for you, the listener, the key takeaway here is that quantum computing isn't just about making computers faster.
Right.
It's about a fundamentally different way of computing, one that leverages the weirdness of quantum mechanics to solve problems that are just impossible right now.
Yeah. And the source is clear that this is still a work in progress. We have a lot of challenges to overcome.
Like those fragile quantum states and figuring out how to build these systems at scale.
Exactly. And quantum error correction is still a big hurdle. But if we can solve these problems, the potential is huge.
Absolutely huge. And it leaves us with a lot to think about, because if we can control and manipulate matter and information at the quantum level, Well, that raises some big questions.
It does.
So, here's a final thought for you to ponder. As this technology develops and becomes more accessible, how do you think it will change the way we approach problem solving and innovation? What new possibilities will it unlock? And how will we use this power to shape the future?
Good questions.
Yeah,
A lot to consider.
definitely a lot to consider.